Welcome back. All right, today we're tackling something huge in the world of AI. It's all about trust. How do we know if we can actually believe in AI when it tells us it's confident about a decision? All right, so here's what we've got on tap. We're going to kick things off with why overconfident AI is such a problem. Then we'll get into the nitty-gritty of something called model calibration. We'll look at how it's usually measured, and then, this is the cool part, we'll dive into a brand new way to measure it. And finally, we'll see why all this really matters in the real world. First up, overconfident AIs. So why is this such a big deal anyway? Well, it really comes down to just how much we're starting to rely on these systems for, well, for pretty much everything. I mean, think about it. AI isn't just for recommending movies anymore. We're talking about systems that make critical, high-stakes decisions. So the question becomes, can we really trust an AI's confidence when the stakes are that high? And that's the heart of the issue, right? We're talking about things like self-driving cars or tools that help doctors diagnose diseases. In these situations, a wrong answer isn't just an inconvenience. It can be life or death. So accuracy alone just doesn't cut it. We need these models to be honest about their own uncertainty. They need to know what they don't know. Okay, so that brings us to the core concept of this whole paper, something called model calibration. It sounds a little technical, but the idea is actually pretty simple. It's all about making sure an AI's confidence is actually meaningful. So what does a calibrated model look like? Well, to put it simply, if a model tells you it's 90% confident about something, it should be right about 90% of the time. That's it. Its confidence actually matches its real-world accuracy. No bluffing. And this is a perfect example of what we're talking about. Look at the uncalibrated model on the left. It says there's a 10% chance of heart disease, but in reality, it's 30%. That's not just wrong, it's dangerously misleading. Now, look at the calibrated model on the right. It says 10%, and guess what? It is 10%. That's a number a doctor can actually trust and use to make a decision. See the difference? It's huge. So, we know what good calibration looks like, but how do we actually measure it? How do you put a number on something like trustworthiness? Well, the standard way to do this is with a metric called the expected calibration error, or ECE for short. Basically, it just measures the gap between a model's confidence and its actual accuracy. A perfect score would be an ECE of 0. So, yeah, the lower the ECE, the better. But here's where it gets tricky. The ECE score we get is only based on a limited, finite dataset, right? So it's not the true error, it's just an estimate. And that estimate can be biased or noisy, just because we don't have infinite data to test on. So that leads to the big question this paper tackles. If we calculate an ECE score, how much should we trust that score? What's the real range of possible error? A single number just isn't enough. What we really need is something called a confidence interval. Basically, a plausible range that says, okay, the true error is probably somewhere in here. And that is exactly what this paper delivers. It's a brand new, much better way to create that confidence interval. So how did they do it? It's a really clever three-step method. First, they came up with what's called a de-biased estimator for the ECE. Think of it as a smarter calculation that corrects for some of the known problems. Second, they did the heavy lifting with the math to prove how this new estimate behaves. And third, they used all that work to build a new, much more accurate confidence interval that really tightens up our understanding of the model's behavior. And you can see the results right here. Look at the difference. The bars for older methods like bootstrap and subsampling are pretty wide, but their new method, that interval is way shorter. And a shorter interval is exactly what you want. Why does that matter? Because shorter intervals mean more precision. We get a much tighter, more useful estimate of the true calibration error. A wide, sloppy interval basically tells us, the error could be somewhere in this giant range, which is pretty useless. A tight interval gives us something we can actually work with. Okay, so this all sounds great in theory, but let's get to the really cool part, putting this method to the test in the real world. So the researchers took an AI model designed to help predict Alzheimer's disease. Now, check this out. When they used the old bootstrap method, it spat out a confidence interval that went from about 3% up to 11%. The key thing here is that the number 0 isn't in that range. So, the bootstrap method's conclusion, this model is definitely miscalibrated. It's flawed. But then they ran their new method. And look at that interval. It includes 0. What does that mean? It means we can no longer say for sure that the model is miscalibrated. In fact, for all we know, it could be perfectly calibrated. This is a completely different conclusion. One method says the model is broken. The new method says, hold on, this model might actually be trustworthy. And this really drives the point home. The tool you use to measure trust can literally change your conclusion about an AI. It's the difference between throwing out a potentially life-saving model for no good reason, or even worse, deploying a flawed one because your measurement tool gave you a false sense of security. Okay, let's zoom out for a second and think about what this all means for the future of AI. Look, at the end of the day, this research gives us a much better toolkit for building trustworthy AI. We're talking about a more rigorous way to evaluate our models. It's faster than the old methods, and it gives us these tighter, more precise confidence intervals. It helps everyone, from developers to regulators, make smarter decisions and avoid being misled by flawed measurements. This is how we make sure that as AI gets more powerful, it also gets more reliable. And really, that's what it's all about. As AI starts making more and more of these critical, life-or-death decisions, how are we going to make sure its confidence isn't just a wild guess, but something we can actually count on? This work is a huge step in that direction. Thanks for joining me on this explainer.